Welcome to 2.7, the mole and chemical formulas. This is the last of chapter 2. Chemists just love the mole. This is millimole from the acs.org site. You can find a lot of fun stuff up there. National Mole Day is actually the 23rd of October, and you can find tons of videos up online expressing things about the mole. Okay, so let's look at some compounds. For instance, H2O. Basically, that's saying for every 2 hydrogens, I have 1 oxygen, or a 2-to-1 ratio. We can also do it for things like carbon dioxide. Carbon dioxide has, for every 1 carbon, we get or need 2 oxygens. So this one has a 1-to-2 ratio rather than the 2-to-1 that hydrogen had. We can go through many others. For instance, CH4, which is methane. For every 1 carbon, there are 4 hydrogens, so it's a 1-to-4 ratio. In doing this, we can say for every mole of water, there are 2 moles of hydrogen and 1 mole of oxygen. For every 1 mole of CO2, there is 1 mole of carbon and 2 moles of oxygen. For every 1 mole of CH4, there is 1 mole of carbon and there is 4 moles of hydrogen. Remember that each mole represents 6.02 times 10 to the 23rd atoms of an element, or 6.02 times 10 to the 23rd molecules. So if we have a molecule, when we break it up, it would become atoms. So for instance, in the CH4, I have 6.02 atoms of carbon, but I have 4 times 6.02 times 10 to the 23rd atoms of hydrogen in the 1 molecule of CH4. Say you were given a mole of cats. How many moles of tails, feet, and eyes would you have? Well, for every 1 cat, remember, a mole is equal to 6.02 times 10 to the 23rd molecules. Now, if we were to say that, then we would know really quickly that 2 moles would be equal to twice that much, which would be 12.04 times 10 to the 23rd molecules. Or if you did it in correct significant or scientific notation, 1.204 times 10 to the 24 molecules. Okay, so if we look at 0.5 moles of NH3, for every 1 mole of NH3, I would have 1 mole of nitrogen. I would also, for every 1 mole of NH3, have 3 moles of hydrogen. So if I look at this, for every 1 mole, or 0.5 moles of NH3, then I would have 0.5 moles of nitrogen, looking at the 1-to-1 ratio. Over here for hydrogen, for every 0.5 moles of NH3, I would have 1.5 moles of hydrogen, which is double. Okay, so these would be the number of moles of each that I would have. So looking at this a little bit further, if you go a little bit farther, 0.5 moles of nitrogen is equal to 0.5 times 6.02 times 10 to the 23rd, atoms of nitrogen. Or over here we go 1.5 times the 6.02 times 10 to the 23rd atoms of hydrogen. Okay, so in your book on page 61, there's a bunch of steps that you can go through to get your ratios that you need to convert back and forth. In the purple, you're working with just elements. In the green, you're working with compounds. Step 1, basically same. Begin with 1 mole of the molecule. Step 2, remember that 6.02 times 10 to the 23rd is your number. If you have elements, that's purple, you say that they're atoms. If you have a molecule, which is a group of atoms, or a compound, which is a group of atoms, you call it a molecule. Step 3, remember to look at the mass that one of those atoms would weigh. And step 3 for the green, or the compounds, you need to make sure you add that compound's mass up to make sure that it's equal. Alright, looking at CO2. Remember, as we do it, to add up the mass, carbon is equal to 12.011. Oxygen is equal to 2 times 16.00. So we would end up here with 32.00 and 12.011 for a total of 44.011 grams in 1 mole. Now to find percent composition, you just take each part over the whole. So if I was to find the percent composition of carbon, I would just take the mass of carbon right here on the top, 12.011, and divide it by the whole, or everything that was added up, 44.011, and then I times that answer by 100, and that will give me the percent of carbon. Go ahead and try that. And you do the same thing for oxygen. For the percent of oxygen, it should be the 32.00 divided by the total mass, 44.011, times it by 100, and that will give me my percent oxygen. Now once I've got these two percents, they should add up to 100.00. Report your percents to 2 after the decimal, and you should be within 0.01. For the carbon, I got 27.29. For the oxygen, I got 72.71%. You add those together and you would get 100. Besides percent composition, this is also known as mass percent. So if you see it listed as mass percent, that's another way to look at it. Okay, let's do another mass percent or percent composition where we've got a little bit more complex molecule, C6H12O6. Same setup. So carbon. Then you're going to add those up. I got 180.162. Now at this point what you want to do is you want to take and divide to get the percent. You're going to take and divide each of these by that 180.162 and then times it by 100 to get the percent. So divide each by 180.162 and then times it by 100 to get percent. And same thing here, divide by 180.162 times 100 to get percent. And I like to set it up this way because I can see quickly what I've got, and I don't necessarily have to write this part right here, okay? Because once I've got this down here, I know I'm just going to take each of those and divide it by that and then times it by 100. So let's look at the percent that we would get. Go ahead and pause the video and try and get the percent yourself. Okay, for carbon I got 40.00%. For hydrogen I got 6.71%. And for oxygen I got 53.28%. So if we're adding all that together, we're going to get 100.00%. That's all for this chapter, and hope you enjoyed the mole.